Hello internet, welcome to our part 2 of the series make your own square root method. Alright, so in this part, instead of guessing and checking or making a better guess, instead we are going to search for the square root, because one thing for sure, we know the square root of any number. Let's say 49. Right, start from 0, lie between 0 and 49. Yes, of course, you can get square root of 49 from 0 to 49 in this range. So what we are going to do instead of guessing random numbers in this range, we're going to search one by one. You can search by a step, let's say one at a time. You can search for 1, check whether 1 is the square root, no. Then 2, whether 2 is the square root, no. We keep on searching until we found the square root. 7, then we stop and then execute that, conclude that yeah, 7 is the square root of 49. Else, like if we want to find the square root of imperfect square root, like square root of a number that does not exist, like 40, if we start from 1, keep checking, 2, 3, let me just write it, 2, 3, we keep on checking. At 7 here, we can conclude that square root of 40 does not exist, or 40 is not a perfect square root, because we know that 7 times 7 is going to give you a number more than 40. So searching ahead is going to be of no sense. It does not make sense. You will never find the square root. So you can conclude at this stage that yeah, 40 is not a perfect square root. It is. We can also reduce our step by, instead of using whole number 1, 2, 3, can go ahead with 0 point maybe 0001, then 0.0002, 3, 4, 5. We will be changing this, right? So let's say that in code. So we're going to create our method public static. For now, I'm going to return nothing, void. Let me just call it square root, and it's going to take in double A, and yeah, we're going to put our logic here. So before we go further, let me show you the square root method in Java. If we come to Java documentation here, this is the square root method. Here is the method definition. It returns in double, and it taking double value A. So you can read this from the Java documentation, right? So this is the parameter taking A value and return a positive square root of A if the argument is none, NaN, or less than 0, the result is none. So we're going to implement this in our second version, in our second method. For now, we're just going to see how we can search for the square root, and this method is not efficient, right? We're going to make it better once we have the better version. We're going to implement it exactly as Java documentation specify. Right? Okay. So for now, let's have a variable double ans. I'm going to call it ans. Our answer is going to start from 0. Right? So assuming a square root of any number start from 0, to the number, right? So we can keep on searching while ans. Sorry, what did I do wrong? While ans times ans is not equal to A, and then increment ans. This time we are going one step at a time. So here at the end of this, we can check whether it is this perfect square root or not. So if ans times ans is not equal to A, we can conclude that it is not a perfect square root. So I'm going to print the number A is not a perfect square root, right? Else it is a square root. It is a perfect square root. Print. Oh, I'm going to say square root of. Oh, I'm going to say ans is the square root of A. Yeah. So but here let's ensure that we always found an answer, or we stop once we can get to the square root. So I'm going to put another condition: ans times ans cannot be more than a, right? So that it will always stop. If not, if this condition was not there, if you pass in imperfect square root, it will keep on sliding because this will never match. So it will be an infinite loop. So let's test this. Instead of hello world, I'm gonna print square. I don't think I need a print method here. So let me delete this, Control D, and yeah, square root, passing maybe 40. We know that 40 is not a perfect square root, so let's run that and see. Yeah, okay, 40 is not a perfect square root. So if you pass it a perfect square root, let's say 49, we will find the result. Yep, 7 is the square root of 49. Alright, so earlier I told you that increment does not have to be only one at a time. Maybe it does not always have to be 1, 2, 3, 4. It can be 2, 4, 6, 8, maybe 3, 6, 9, 12, 15. Yeah, so whatever increment you wanted to increment it by. So in this case, I'm going to let's try 0.001. So the lower the increment, the more step it is going to take to complete running the code, but the more accurate the result will be. So our increment is going to be 0.001, right? So if we run this, let me save it and run it. We're going to get 49 is not a perfect square root. Yeah, and 49 was in fact a perfect square root. So why this? Let me show you this. I'm going to print the answer that we got. I'm also going to print yep, the answer times itself, what it is going to give us. And third one is going to be the difference between the ans and the value that was passing. Right, so let's see this in action. I'm going to expand this. Look at that, we got 7 as the square root. So 7 this one times itself is going to give us this, and you know we were looking for exact match. So 7 times 7 is equal to 49, while this one 7.009 something with this result times itself is going to give us this one here. 49.0014 whatsoever is not equal to 49 exactly, right? So that's the difference is this 0.0014. So what we are going to do to fix this is here. If you look at this differences, it's just something close to our epsilon, right? So what we can do is this: instead of looking for an exact match, we can put these differences into a variable called epsilon, right? So that this epsilon is going to be 0.001. Epsilon does not have to be always equal to your increment, but I'm going to make them equals. Yes. So instead of the exact match, what I'm going to do here, I'm going to look for the differences, not just differences but the absolute differences. Mass.abs, the absolute difference between ans times ans minus a, as long as that is greater than or equals to our epsilon, then keep incrementing by whatever the increment is. In this case is epsilon, right? So I'm going to copy from here all the way here. I'm going to check that here. Instead of checking for the exact match, I'm going to check for this. So long as the difference is greater or equals to the epsilon, then it is not a perfect square root. Just like this, if the difference is more than this, in 49 for our case, if the difference is more than this one, this is our epsilon, then it is not a perfect square root. So if it is confusing, take time to meditate. Hopefully it will sink in. So look at that, we saw that 7.00672 is the square root of 49. So since we are not looking for the exact match, I think the good sentence is going to be this is close to the square root, not is the square root, is close to the square root. Let me enable soft wrap here. Soft. Yep. We're good to go. So it's going to be is close to the square root of instead of is the square root of. I think I need to extend that. It's close to the square root of 49. Yeah, so now let us take this to the next level by introducing binary search. I'm going to create the same method, public static void. This time I'm going to return double, and I'm going to call it square root. Yep, it's going to take in double A. Yes, it's going to 1 here. Let me just change this to square root 1. Right. So in here, let's define our double ans, our double variable ans, which is going to hold our result. And in the end, we are going to return this ans. But now I do not know what the answer will be. So let me show you this in whiteboard. Let's discuss about it. In here, if we want to find the square root of, I cannot see my mouse. If we want to find the square root of 49, right? Let me write it here. 49. We know the square root of 49 lies from 0 to 49, right? So what we could do is to, instead of searching one by one, we could just use this algorithm called binary search, dividing and conquering, meaning reducing our problem by half at every step. What I mean is this: square root of 49 is, we don't know, so let's start searching from half. So and half of this is how much? 49 divided by 2, that's 24, right? Yeah, so we can put this into a condition. We can check whether 24 is the square root of 49. No, but in fact searching from 24 and above is going to be waste of time. So square root of 49 will not fall anywhere from 24 to the right hand side. So we have reduced our range. Instead of from 0 to 49, it is now from 0 to 24. So if we repeat the same step here, if I say 24 divided by 2, I think that's 12. Am I right? 24 divided by 2, that's 12. Yeah. So we put this again into a condition and we check. We realize no, 12 is not is more than the square root of 49. So square root of 49 cannot be found from 12 and above. Now we have reduced our side time again to half. Our new side time is from 0 to 12. So here, if we repeat this step, we have 6, right? So 6 is not the square root of 49, and in fact from 6 and below, square root of 49 is not going to be found anywhere from 6 and below. So our side term is now from 6 to 12, right? So 6 to 12, the range there is 9. If we put 9 into the condition, we realize that it cannot be found anywhere here. We repeat this step again. So now it's from 6 to 9 instead of 6 to 12. So 6 to 9, that is 15. I think 15 divided by 2, that is 7. Right? So we can conclude that, yeah, 7 is the square root of 49. So what we are doing here is we are reducing our problem by half at every step. First, our range was from 0 to 49, so we reduced by half. So we are not going to search this right hand side again. We know, because we know exactly the square root of 49 is not going to be in that range. So our range has reduced to from 0 to 24. We do the same thing, right, until we found the square root of 49, which is 7. So now let's implement that method here. What we are going to do is this: while ans is not, it's going to be the same thing. While ans times ans, in fact, the absolute difference is ups. Why am I doing y ans? I'm not looking for an exact match here. I'm just looking how close. I've said that in the guess method. In fact, in our first square root method, I do not emphasize epsilon that much, but it is because it's going to be repetitive, so that's why I do not emphasize. But we are looking for how close. So to look for how close, we are going to check if our epsilon our differences, the absolute difference between our square root ans times ans and the number, if it is greater or equals to the epsilon, then we keep on searching. Let me define epsilon up here. Double epsilon is equals to 0.00000. I do not know how many zero for now. And once it is greater than this, we keep on searching. So, but this time, this searching is not just going to be random search or linear search. It's going to be binary search, as we demonstrated in the whiteboard. So in there, I don't know if you notice, we have two places, left and right. Let me show you. For instance, 0 to 49, our left is, this is our left, 0 is our left hand side, and 49 is right hand side. So once we decide we have to focus on, we just update either right or left. In this case, once we find out right, we are going to ignore the right hand side. We updated this thing right. So right is now 24. Our new range stop at 24 from now left to right, something like that. So I'm using those two variables here. So our left start from 0, right, and our right start from the A. The mid, which seem to be the ans, let me just separate it and call it mid, is going to be ans, is going to be, sorry, left plus right divided by 2. Right. What did I do? Yeah, we are good to go. Yeah, so this is our mid. We will need this in our while loop because it's going to be calculating mid every time. So we need to tell when which side to search. That is where to ignore, where to search. If ans times ans, if that is less than A, what do we do? If, for instance, here again, when we found 6, so 6 times 6, that is less than the square root, we are trying to find 6 times 6 is less than 49, right? So we know we are going to ignore left hand side, right? So the same thing apply here. If ans times ans is less than A, ignore left side. So which mean simply update left, meaning it means literally we are ignoring left hand side. I'm repeating myself, but that's okay. We are ignoring left hand side, so we are updating the left pointer from, instead of 0 to 6. It's now, the range is now going to be from 6 to 12. That is what I'm trying to showcase here. And else we ignore, of course, if we are not ignoring, if we were ignoring left, now we are going to, else we are going to ignore right. Right, so ignoring right is simply updating right, as in this case. Let me show you again. As in this case here, ignoring right is just like updating the right point of R here, right, instead of from 49 to be 24 to be mid. That's exactly what I'm doing here in code. So that's all what we need. So I think we are done. Oh, sorry, I forgot to update ans, which we should, or else we run into an infinitive loop. So ans should be equal to mid at every iteration. So what is the intuition to that? If this seems redundant to you, that's completely okay. I did it on purpose. I just separate ans from the mid. Yeah. So this is the middle of the element. We are checking if the middle of the element is our square root. So this is the mid. So we're saying our answer is this. We will not conclude yet until we run out of this while loop. So once we run out of this while loop, then the answer will be equal to the square root of the number, or so close, something like that. We are using ans here. We could use just only mid instead of ans, but I just separated on purpose to separate the logic, the mid from the ans. I don't know if you get what I'm saying. I just hope I'm communicating. Yeah, so that's it. Let's test our method. I'm going to print it square root and pass in 49 for the square root. Let's run that and see. We got 7.00 with something decimal for 6118. So the more accurate we want our answer to be, the less we should make our epsilon. So the lesser our epsilon get, the more accurate our square root or our result. Right? So let's make it let's make it lesser. Yeah, so we got 7.0. Finally, let me see if epsilon, the smaller the epsilon, the more step it take, but the more accurate. Yeah, so 40888484, that's what I want to put. 40888484. This will give us 2022. Yeah, because I wanted 2022 subscribers in this month, so help me get there. Oh, my bad, I forgot to handle the negative and NaN cases as it was specified here in Java documentation. Return the percentage square root of a if the argument is not a number or less than 0, the result is not a number. So let's implement that. If a is less than 0, meaning negative, if it is less than 0, or the argument, if the argument is none. So to check whether it is none, double dot is method, then we pass in a. If this is true, we're going to return yeah, we're going to return none. So that is none. Right now we need to import none from java.lang.double.none. Right. So let's see it up here. This is what we just import. So this is all what we need for this. Let me make it beginner friendly. So that is what I was doing since. Yeah. So we can pass in. If we pass in negative, let's see what we got. We will get none. Yeah. By the way, thank you for watching, and I'll catch you. Yeah. I hope you learned something from me. I love you.